We have Fred Baker, who is our first speaker. And, you know, I don't even need to look at the notes to talk about Fred. You know, and I'm going to tell you a personal story about Fred. Fred is one of the first people that I met at the IETF. He has an incredible history. He was IETF chair. He has, I don't know how many RFCs, I'm sure over 60 RFCs, numerous patents. He has we just go to his Wikipedia page. If you Google Fred Baker, you'll find it. And one of the things I found about Fred is if I'm ever confused about something, I'm like, how in the world did this ever happen? You know, it's like, why did we not have a transition mechanism at this point? Fred knows the history. Just even this morning, we were talking about, okay, so I see one country doing various things, and he's like, let me tell you about the history of that country's participation in the IETF for the last 10 years. And it's incredible. He knows, he's such a fount of knowledge and history. It's incredible. But also, too, he's one of the nicest people that I know. He has mentored so many people that it's just incredible, and including me. I remember when we had a very difficult first initiation into the IETF. I was nearly in tears for the first 2 years in trying to present this draft. And it's people like Fred who said, keep going, it's an important thing, that's allowed me to keep going with the IETF. So Fred, thank you so much, and let's have you come up.
I've already.
Yes, the thing, okay.
Okay, thank you, Delaney. So I only have 54 seconds left? That's
4 minutes.
Oh, okay. So, okay, I've been asked a number of times, kind of, could you run over the history of the internet? And so I prepared this talk actually for the Internet Society and for their policy program.
The below one.
Huh?
The one below.
The one below.
That's the one.
There we go. Okay. So I want to talk a little bit about how we got here, and understand that it's not like somebody said, let's have an internet. And no, that didn't happen. But there was a lot of different projects and people involved in them, and ideas. Ideas that differ. So this that I'm going to talk about is not the story of one particular person, or so-and-so is the father of the internet or whatever, but it's going to be kind of weaving together a number of stories and a number of thought processes and experiments that have gone on. And so I'm going to try to tell what is really a very complex story. So I think it starts out really with an MIT professor by the name of J.C.R. Licklider, who liked to sit down with his students and imagine. Can you imagine walking up to a computer? And this is what a computer looked like in 1962. This particular one ran SAGE, which was the North American Air Defense System. It was a huge computer, filled a room, and consumed lots of electricity. Can you imagine walking up to a computer and asking a question, random question, whatever question that might be, and the computer answers? And you can find all of the information of the universe talking to this computer. This picture that I have in the lower right-hand corner is from a movie. It's from Star Trek 4, I think. The Star Trek team is transported in time back to the mid-1990s and has to go save a whale or something like that. And so the chief engineer, Scotty, finds himself having to deal with one of the computers of the day, which happens to be a Macintosh. And because he, of course, talks to his computer, what he does is he picks up the mouse and he says, "Computer," and expecting the computer to answer. And the guys behind him are, this guy's weird. Okay, but this is what J.C.R. Licklider was imagining. He's saying, imagine he could walk up to a computer and say, whatever, and the computer would answer and give you all of the information of the universe. Now, packet switching as we do in the internet, came from one of his students, a fellow by the name of Len Kleinrock, who did his doctoral paper, thesis, whatever you call it, on this concept of packet switching, and then several exploratory efforts that were done in different places around the world, separate efforts. People weren't really talking with each other, but let's try this idea out. What happens if I switch packets? So the work that Len Kleinrock did, his lab in the 1960s at UCLA, then basically built up and ultimately deployed to the ARPANET, which is the basis for the internet as we know it today. Paul Barron was also working at the same time in a think tank called RAND. The think tank is primarily military focused. And so his study, his paper, and it's literally just a paper, he didn't try anything out. But this picture that you see here is lifted out of that paper. Okay, and he was kind of saying there could be lots of different kinds of networks. And maybe I could run voice, what we would today call voice on IP, but packet switch voice across these various different kinds of networks. And well, what would happen if something broke? And you know, working through all of those issues. About the same time, 1965, in the United Kingdom, there was a fellow by the name of Don Davies, who was working at UCL, which I think IBM was a big computer manufacturer at the time, and was also kind of picking up on that concept, not really communicating with Barron or with Kleinrock, but you know, let's go play with that. What does this actually consist of? And he's actually the guy that first, Barron was the guy that called the things that were passed around packets. And Davies was the guy that called the process they were doing packet switching. I've been doing packet switching most of my adult life. Okay. So, now then in 1969, in 1968, Larry Roberts was a program manager at DARPA. Let me tell you a little bit about the Defense Advanced Research Projects Agency. Why do we have it? What does it exist? What is its mandate? I hear from a lot of people, the internet was designed to support military applications. It's not true. Not true at all. It was funded using money that was done for military research. But here's the deal. So if I look at the American Revolution, I've got people running around with rifled muskets. And the British Army was using a Brown Bess, not rifled musket, just a smoothbore musket. And so the colonists could shoot farther and more accurately using their rifled muskets than the British Army could. And that wound up being important in the American Revolution. If I go to the American Civil War, there was some guy by the name of Gatlin that came up with a gun that would shoot and shoot and shoot as long as you could turn the crank. And that became important in warfare. If I go to World War I, had people in trenches pointing guns at each other, and the British said, you know, it would be really useful if I could put something out there that you could shoot at all day and it wouldn't be hurt. Let's call it, for purposes of security, let's give it a name that nobody knows what this is. We'll call it a water tank. And, well, it became what we now know as a tank. And could roll across a battlefield, and of course both sides had to agree to it. And it changed modern warfare. We get to World War II. Let's fly planes and drop bombs on cities. Let's build the atomic bomb. Let's do all of these different things, which became important in the progress of World War II. After World War II was over, then the U.S. Department of the Army was reorganized as the Department of Defense. And they said, we've had enough of this. each war, we have a technological surprise that changes the war. Let's not have if we're going to have a technological surprise, let's us be the people doing the surprising. And so they set up the Defense Advanced Research Projects Agency with the idea that, okay, you see somebody doing research somewhere, fund them, give them money, figure out what that research is. If it has a military application, okay, go use it. If it doesn't, give it back to the civilians. But let's push research for the purpose of forestalling technological surprise in warfare. Okay, so now Larry Roberts is a program manager with the Defense Advanced Research Projects Agency, and he's reading Kleinrock's paper, he's seeing these other things going on, he says, can I give you guys some money? You know, go figure it out, and we'll talk about later what there might be as far as the use. And well, sure enough, they built what we now call the ARPANET, or what at the time we called the Advanced Research Projects Agency Network, and started connecting institutions, learning institutions. And the first packet was sent across the ARPANET from UCLA to Stanford Research Institute, which was in the San Francisco area. And that was actually an intent. The idea was to log into a computer. Here's the experiment. Let's log into this computer and see what's going on. And the thing is that they got kind of halfway through logging in and the computer crashed. Okay, but that was the first communication across the what we now call the internet. Now, another thing that happened about that same time frame from one of the researchers that was working at UCLA, Nalini talked about RFCs we love. Well, you know what an RFC is? Say, request for comments. Why did Steve call them requests for comments? He wanted to not draw attention to them, but provide a way for researchers to talk with each other, to document whatever they were thinking and make comments on it. Vendors later called them requirements for compliance, which is to say specifications. But yeah, so that's where RFCs came from. It was, hi, we're just a bunch of guys. Can we share notes with each other, guys and gals? An important change came in 1970. So this is very early, just a year after that first packet exchange on the ARPANET. What happened, they built a network that went all around the Pacific Ocean and connected through a packet processor located at the University of Hawaii. Now, in Hawaiian, in the Hawaiian language, aloha means hello, and it also means goodbye. It's just a standard greeting. And they refer to it, because of the Hawaiian center of the network, they refer to it as the Aloha Network. It was an interesting thing in that, now, if I do something through space, going through a geosynchronous satellite, and I do that at the equator, just sending the packet and getting it arrived at the other end takes 172 milliseconds. If I want to have a response, that's another 172 milliseconds. And the idea of coordinating these computers so that they would send things so they didn't bump into each other, they thought about that for a long time. And they finally said, that's too hard. Let's not do that. Let's instead just say, okay, these computers will send packets whenever they think of them at a random time. And if they don't happen to get through, well, they'll send it again. That was an important concept that communications had not run into before. Of course, end to end, I will know whether the packet arrives. And this was a network in which they said, suppose I don't. Suppose I don't. That ultimately became what we use for congestion control in the 10 megabit Ethernet. That's kind of where that came from. Another thing that happened along that time, now communications up until that point had always been across a circuit, something that was a wire or that looked an awful lot like a wire in many respects. Louis Poisson in France, said, what if in the packet I put some information so that the packet knew where it was going and where it came from, so that we can now set up a conversation without having to set up a circuit. And so if I look at a postal letter, I have this concept. I know where the packet came from. I know where the packet is going to. The postman can pick it up and say, okay, fine, do this. And Louis said, well, what if we did that in the internet? And started experimenting with that concept in the French counterpart, or the equivalent of the ARPANET, called ICANN in France. And this, of course, has become very important in the internet of today. Now, let's think about, how do I route data? If I am a router and I'm just talking with another router across a local area network of some kind, I know where the other guy is because he has an address at the MAC layer, and I know what interface his packet came in from. And so what I'm going to do is I'm going to send a packet to that address on that interface, and it'll get there. I know that. Okay, so I can talk about there being a dedicated link or a circuit of some kind. And then in the more general sense, packet switch, I put the address in there and it goes. If I take those concepts and put them on a roadmap, surprise, surprise, we use this concept, or we use this set of concepts in just driving a car or whatever. So if I'm starting from Delhi and I want to go to Kolkata, I don't know why I'd want to do that. If I did, one of the things that I could do, that upper gray line is an airplane. That's how Google Maps represents an airplane flight. And that's an awful lot like a circuit. I know where the plane's going, I load people, whatever, on the airplane, and when it arrives at the other place, they all get off. I know exactly where that's going because of the circuit, okay? The lower gray line is actually a train route. I know what route the train follows, and I can kind of make the same thing. Or if I'm driving a car, I can hand a map to the driver and say, okay, you're going to Kolkata, figure it out. And the guy continues and goes on his way. Now, if I look at routing for calls and data, what I can do, I can name the route. I can say, get on the plane, or I can say, get on the train, and then follow that to the end, where you get off. We use that today in the internet in MPLS. We use that basically anywhere that we do circuit switching of any kind. And we have a number of places where we use that. Okay. Or in IP, I give the packet the destination address that it's going to, and it can follow a map, it can follow routing and get there. Okay. So those concepts turn out to be, by analogy, they're actually pretty familiar to us. And so we've taken those at the next step to go on. Hello? There we go. Okay, so now I've taken you up to 1972. 1972, I was a sophomore in college. No, I didn't invent this. My kids tell me that I invented dirt. But this whole concept was demonstrated at a conference called ICCC by another ARPA program manager by the name of Bob Kahn. Bob Kahn is still around. He runs CNRI, and they do research projects around the Washington, D.C. area. The application that he demonstrated is one that you've all used. It's called Mail. And he came up with the concept of, okay, I need to be able to name a computer, I need to be able to name a user ID on that computer, get a packet somehow to that. It goes long. And so we use that to give an address and email. And really, for probably 20 years, mail was the killer application that made the internet be interesting and useful. when it came to using the internet in the mid-1990s, my mother started using it because she discovered she could do that and her grandchildren would reply. And I'm like, okay, fine, off she went. But okay, there was the original Telnet specification and the development of something called the International Networking Working Group. Now, how many of you have read an RFC? How many of you have seen words at the top of the RFC saying it was produced by the Network Working Group? And wondered where that came from? Now you know. Okay. Okay. Now, in his talk at ICCC, Khan talked about what to his audience was a very strange kind of network. You know, why would you do this kind of thing? And he set 4 major ground rules for this network. He said that each distinct network, by which he meant the college at the periphery or whatever, would set up its own rules and was autonomous from all of the others. And so if we connected a new college to this ARPANET, we didn't have to change the college. It needed to run IP, it needed to run ICMP, ICANN. But beyond that, it was autonomous. It could do kind of whatever it needed to do. All communications would be on a best effort basis. Best effort means you're allowed to bend, fold, spindle, and mutilate every packet. This has been described as handing your data to the enemy and hoping he does the right thing. That was a completely revolutionary concept at the time because communications was always done with a service provider, and the service provider guaranteed an uninterrupted path. The data would arrive, it would arrive in order, it would all get there. And Bob Kahn said, what if it doesn't? You know, how do we resolve those issues? How do we deal with that? And as a result, how do we simplify the network and make it more deployable? They would use black boxes, what today we would call a router or a gateway, in order to connect to the internet. And these boxes, oh my goodness, had no per flow state. They didn't have connections to each other. And that was a revolutionary concept. He had a lot of people mad at him as he was giving this talk. And there would be no global operational control. A government couldn't come in and turn it off. If you could imagine a network where that was a question. Okay. So in the following, starting in 1973 and really continuing through perhaps 1980, there was a fair amount of work done in the research community looking at this and saying, okay, this is a good prototype, it works, but maybe there's something better we could do. How can we improve that? And so they, various people, one of them, you probably all heard of VinSurf. VinSurf was an important driver in this area. Separated the MCP protocol into TCP and IP. That worked well for certain applications, didn't work so well for others, so they came up with a new protocol. It's called UDP for those applications that needed that kind of control at the application layer. Went through an update process and ultimately issued RFC 791-2-3. Now, RFC 791 was first deployed operationally in Korea by Kilman Chung. And so he had that running among a few computers there. And then in 1973, it was turned on in the ARPANET of the time in the United States. So the killer applications at the time remained mail, remote login, and file transfer until the World Wide Web came about, which was an interesting game in itself. So I just said this. Now, one of the things that happened then was the SRI, the Stanford Research Institute, now Science Research International, but it's changed name, would every week, every few days, post a file and people would download it. You know, if you want to know what the hosts are on the internet, here are their names, here are their addresses, and here's how you get to them. In 1987, there were 173 such names in the host file. And that was considered huge and voluminous, and what are we going to do with all of this stuff? And so there was a fellow by the name of Paul Petros who said, well, there's got to be a better way to do this than having a host file. Came up with what we now call the domain name system, which was a hierarchical and scalable approach to naming and translating names into addresses for the internet. Okay, now how many of you have heard that Al Gore invented the internet? Let me tell you a story. In 1955, Al Gore Sr. was the senior senator from Tennessee and was a very important mover and shaker behind the United States national highway system. We had, in World War II, learned to move materials by truck across Europe and across Japan, or across the Pacific region. The Burma Road is a very famous instance of moving things by truck. And folks kind of said, well, you know, we've learned how to do this. Could we possibly use it for interstate commerce? And, well, the way the roads were in 1950, it'd be really hard because the roads went kind of wherever they went. And so Al Gore Sr. said, I have this crazy idea. Let's imagine that we build a road that goes from Jacksonville, Florida to Santa Monica, California. And it's big enough to carry all the traffic that goes there. We'll call that Interstate 10. And we'll build another one that goes across the middle of the United States. We'll call it Interstate 40. And across the northern border, we'll call that one Interstate 90. And north and south, you know, it might be 400 or 410 or something like that. And so basically build a crosshatch pattern across the United States for interstate commerce. Now, how did they convince people to fund that? Well, at the time, what was going on was the Cold War. And I grew up saying, okay, the popular thing for a bunch of students to do as a class, you know, let's go have a field trip kind of a project, was to go to a Nike site, which was where missiles were set to shoot up airplanes coming over the horizon. Imagine your airplanes are coming over the horizon, they're carrying nuclear weapons, one of those goes off. What happens next? Well, there's an electromagnetic pulse, and all of the airplanes in the air immediately fall out of the sky. What if we did something about that? And so in the process of deploying the road system, they said, okay, every 5th mile will have 1 mile that is perfectly straight and can be used as a runway. And now the first roads, not the roads that came later, but the first roads had that characteristic that every 5th mile was perfectly straight and could be used as a runway. Okay, so now Al Gore Jr. in mid-1980s is the junior senator from Tennessee. And I want to do something really cool like Daddy did. And so he came up with something that he called the Information Superhighway. The Information Superhighway was intended to connect six supercomputer centers that had been deployed in various places in the United States. And the idea was now to be able to connect colleges and universities to the supercomputers and enable them to do that. And oh, by the way, maybe we could try out some of these interesting technologies that are being looked at. So an example of that was CSNet, which was run by the University of Delaware, by Father Time, and USAN, which I was involved in. This is the point where I come into the picture. It was basically an Ethernet-based, in a satellite network, connected from the National Center for Atmospheric Research in Boulder, Colorado, and going to 39 universities around the country. And the 56 kilobit NSF net, which in time became the internet as we know it, because everybody wanted to connect to it. And there were a variety of other networks. Okay, so basically Al Gore Jr. went to Congress and got money. And that turned out to be really useful at that particular point in time. Of course, you never have trouble getting money. We in the internet did at the time. And Al Gore, he didn't invent the internet, but he sure helped fund it at a particular point in time. Okay. Now, what are the structures that lived around the internet? Well, one of the important ones was the guys that had been the students of Len Kleinrock and had been working in that time frame. Basically got together and formed something they called the Internet Architecture Board or Advisory Board or whatever. The acronym would stay the same, but the name changed from time to time. And they were the graybeards, the fathers of the internet, if you will. And they got to a point with the deployment of the NSF net and this experiment that Al Gore was driving. Things were just too big for them to handle. And they said, well, what if we set up a bunch of task forces? And most of those task forces collapsed together to become what today we call the Internet Research Task Force. But one of them in particular was for the engineering of the network and the protocols that it would use, and that was called the Internet Engineering Task Force. So at that point, the IAB retained control of RFC publication and the input to the RFC editor queue, but basically it allowed vendors, allowed open source engineers, allowed people to start really contributing to what became the internet. So the IETF has a number of different working groups in different, what we call areas, organizational, that routing, network management, and so on and so forth. So it's a multidisciplinary organization. It's an organization that does a lot of things. And oh, by the way, it draws people from a number of sources, from operators, from academics, from industry, from wherever, which makes it a multi-stakeholder organization as well. This really is where the modern multi-stakeholder model came from. Let's get everybody together and we'll talk about it, whatever that is. Now, I mentioned the research task force. There were, as I mentioned, there were a number of groups. There were originally separate task forces, like the end-to-end task force, which became research groups within the IRTF. And once again, it's a multidisciplinary organization drawing people from all sorts of places, and so it's a multi-stakeholder organization as well. Now, in the 1980s, it was really very confusing and expensive for a company to operate a network. Why? Because everybody was fighting to be the one game on the block. Digital Equipment Corporation ran something called DECnet, and it connected whatever it connected. Apple Computer had its own. Xerox Corporation had a protocol that they had written and designed, which turned out to be used by a number of different other organizations, and so it showed up, this is X and S, and this is X and S, and this is X and S, and this is X and S. And, oh, by the way, MIT had its own chaos net, and so on and so forth. So there were a number of these protocols. The thing they had in common that was interesting was that the address in each one consisted of two parts. It had a network number by which they meant an identifier for an Ethernet cable or something like that, and a host identifier, so it connected the host and the subnet. Now, what started happening at that point was in ISO, there was a project called the Open System Interconnect Development, which came up with a reference model. The reference model is still the set of words that we use to describe what we're doing. Not that what we're doing corresponds to that reference model, but those are the words. That's where the words came from. And of course, the Internet Protocol. And OSI, the CLNP, and IP at the time had an interesting characteristic in that it not only connected to a host and a subnet, but it was able to talk about a network. There was something over there that consisted of hosts and subnets that I might send a packet to. And then when we came up with IP version 6, with a 128-bit address, we're actually able, in the address, to talk about a service provider. We could apply it to a continent if we wanted to. The one thing we don't really talk about in the address is a country. We talk about that in naming, but we don't talk about that in addressing. But the development of the concepts, we talk about connecting to a host on land, and then a host on land that's in the building next door, and then a host on land that's in another company, or something like that. And there's development in thinking and in the technologies that went along with that. And now with this, then in the mid-1990s, at some point, the IT departments in all of the companies that were deploying this said, enough, this is crazy, we can't do this. And they went to their vendors and they said, listen, there's this IP thing, it works. Take your stuff, make it be able to run on whatever that is, that thing, and we'll run that network and connect all the applications using it. And at the point that they did that, all of those things that are in the left-hand column disappeared. They're just gone. It might have taken a year or two, but not very long. But suddenly, everything was IP, and you could run your gaming lines or your, whatever it might be on top of IP, then run it across that network. Now, I mentioned the NSFnet, which in the mid-1980s was a research project, part of the stuff that Al Gore was funding and driving. That, in turn, got replaced. Why? Because people were moving on and were making networks larger and more interesting, and it became obsolete over time. Okay, so we call that general process the commercialization of the internet, and it was a huge change in the network in the 1990s. Let me give you just a picture of that. There's all of the different universities in New York got together and said, okay, we want to connect to the NSFnet, but this is just too crazy. We can't everybody connect to the NSFnet because it is too complex. Why don't we as a state, the state of New York is in the northeast part of the United States, why don't we as a state set up a New York area service network, NYSERNet, and then connect NYSERNet to the NSFnet. We can now talk to each other, and we can efficiently and cost effectively now connect to the NSFnet. So NYSERNet, which by the way still exists, became one of those early regional networks, PSI. It became eventually part of Genuity and part of what is now Verizon, and so on. You run down the list of those different networks, and you can find them today. They've been bought by somebody. Another thing that happened at the time was that the Internet Assigned Number Authority, which is otherwise known as John Postel and Joyce Reynolds, with an army of helpers, decided that the work that was going on in their part of the world was too much. And so they started setting up regional areas that are companies that could go work with the service providers and provide the resources that they needed. The first three we called Aaron and Ripe and APNIC. We now have LACNIC and ARPANET as well. So those regional networks eventually became commercial networks and in turn replaced the structure that had been the internet before. So now I turn to the summer of 1992. In 1992, Casey Claffey, who now runs an organization called CADA, which is where we get a lot of our research information about the internet, was working on her doctoral paper, her thesis. And she did an experiment. She started with the NSFNet and took a feed, several different feeds off it, 5 of them, I believe, and just categorized what an hour's traffic looked like. And she found an hour long of voice on IP in 2 different cases. She found FTP moving traffic. Yeah, she found all sorts of things happening. And she did that once at the beginning of the summer and once again at the end of the summer. At the beginning of the summer, a typical TCP transfer was about 200 packets each way. At the end of the summer, it was more like 15 or 20. Yeah. What in the world? You know, so now she starts drilling down and characterizing that. It turned out a large number of these packets had port number 80. She had to go look around. What in the world is port 80? Oh, it's those guys at CERN. They're running, what do you call it, the World Wide Web. The World Wide Web basically took over in the application area, became 50 or 75% of the traffic on the network for really quite some time. And the browser that we were running at the time was something called Mosaic. Okay, and that became an important part of internet traffic and internet stuff going on. And about the same time then, a professor at University College London and a professor at University of Wisconsin got together. The second one, Larry Landweber, had been running conferences to get people to talk about this internet thing. And they said, well, you know, what if we combine forces and combine forces with the IETF? Will form something that we call the Internet Society. And so some of you have heard of the Internet Society. That's where it came from. And it was really the first recognition that the Internet was more than a toy. And a research project. It became something that was talking about, so how is this going to change commerce? How is this going to change military services? How is this going to change thing after thing after thing? So, so they created the Internet Society. Originally, it had 4 what are called pillars. It talked about public policy, education and training, and standards and protocols, and oh, by the way, membership. Nowadays, they've kind of dropped membership from that list. But they had categories of members, including individual chapter and organizational member. I have been a member of the Internet Society since 1992. They have some interesting things going on. So now I've talked about the networks. I've talked about the routing technologies. I've talked about the addressing technologies. I've talked about the institutions that were developed to manage them. And I've given you a picture kind of some of the applications involved. Something to understand is the internet fundamentally changes its applications every 3 to 5 years. And not that the old ones go away, but we'll add a new one, and all of a sudden, oh, everything going on is video, or is voice on IP, or maybe we talk about IoT, or whatever. We always have something new. And what it does is it adds to the traffic load, which is a good thing, and allows us now to accomplish some new thing. So today, video is like 85 or 90% of the traffic. We're looking at network virtualization. We're looking at distributed telemetry, distributed control, or what we call IoT. And we have new things coming down the pike. We always have new things coming down the pike. So I should have one more bullet there that says insert your name here, because that's important. There's always room for new innovation. Okay, so in the 2000s, we had 1 billion users and we started accessing smartphones and we started talking about internet governance in a big way. And where we are now, we have, if I just look at autonomous systems and what are the autonomous systems in the world, how many of them are there? Well, there's on the order of 60 or 70,000 of them. About 10,000 of them would be described as infrastructure. They connect to this, to that. And then another perhaps 50,000 are the edge things around that network. And we have a large number of users. Right now we reach about half of the world. Okay, now what were Kahn's principles? In 1972, he said, well, each one's going to be autonomous. Has to have an IP address, you know, doing whatever it's doing. Communications is best effort. We connect networks using routers, and there was no global operational control. The interesting thing is that that's still very much true. Even now where we see governments saying, I want my country to no longer be on the internet, there isn't a way to turn it off. The question usually becomes, how much damage does the government do to its country, and destroying commerce and making things difficult for itself and its own people. The primary service in the network is connectivity. And to this day, that remains the most important thing. So, okay, I ran out of slides. But let me just throw this open for questions.
We have mic here. Anybody has any questions?
Don't everybody rush the mics. Okay, there's a question over here.
Can you come to the mic here? Oh, sure. We are following the IETF way of making you good work.
People who are not familiar with the IETF, typically the way it works is in a working group meeting, you have set up like this. You will try to kind of replicate that. So there is a mic, typically it's in the middle, but since we have the video right there, we have to put it here. And if you want to ask questions, you kind of form a line in the mic and kind of ask your questions one after the other. So anytime you want to ask the question, the floor opens for question. My request to you would be to kind of form a line at the mic, and then maybe we can answer those questions one by one. Yeah. Yeah, and when you step up to the mic, probably state your name and maybe affiliation. That would help.
Right. Hi, my name is Pradeep Mishra. I'm from TCS. So this was a fascinating history. Thanks. And my question is, at what point in time did security become a real concern, and were there any specific incidents that triggered that interest?
Well, there's a paper, and I don't have a pointer to it, but there's a paper in 1983 where Vint Cerf talked about something that he tried to do in Internet Protocol and got pushback from the United States government, and that was making cryptography be important to the applications and protocols that ran on the Internet. I wish he had succeeded, but certainly in 1983, people were thinking about that. In 1995, 1996, I was the chair of the IETF, and we were sitting down with people that were promoting RFCs, and I want to publish this document, and document after document after document, we would look at them, and this is going to explode. The bad things are going to happen if anybody actually uses this protocol. And we would sit the authors down and have them explain to us in fairly detailed words. My company is not going to spend the money to deploy a secure product because nobody will pay for it. Okay? And so yes, we were thinking about it. We even had a security area director, and directorate, working groups that were working on that. The thing that we now call IPsec originally started, the work started in 1990. It ultimately got published in 2000 or 2001. We were interested in that, we were concerned about that, but we couldn't push the industry to go do something about that until it started showing up in people's bottom lines. And all of a sudden, now security is right on top of, it's the first question we get on this. And it's not that we weren't thinking about it, it's that people refused to deploy it. Delaney.
Thanks so much, Fred. It's fascinating always to get your perspective on things. I have two questions. Because I know this is something that affects India in particular. Can you talk a little bit about internet shutdowns and just, there's a lot of issues around that for India. And then secondly, how people might get started in participating in the IETF.
Okay, those are two very different questions.
Yes.
Okay, so I'm not going to comment specifically on Kashmir or the things that are going on in India. Of course, I know about them, but I'm not going to get into that in particular. What I will say is that there are a number of countries that have looked at that. Cameroon, for example, has an English language population and a French language population. French language is about a third of the country, English language is 2/3. The government is all French speaking. And the technology community is all English speaking. And so the government at some point decided it wanted to damage its English speaking people, and it shut down the internet. And that lasted for 6 months or 8 months, something like that. Basically as a way for the government to take control of the technological part of the country. The first of those shutdowns happened in Egypt. The Minister of Communications at the time was a fellow by the name of Tariq Campbell, who you may know just recently died, just passed away. And he had been working for years and years and years to try to promote Egypt and make Egypt be important in Northern Africa, and had established communications between Egypt and the internet around the place. I know that because I was involved in some of those efforts. But then somebody with a gun walked into the office and said, "Shut it down." And what do? So it got shut down. And it got shut down in a way that preserved the service contracts with surrounding countries, but made it hard for people within Egypt to talk with whoever they talked with outside of Egypt. And that was basically done with routing. That was done with BGP routing. What do I have to say about that? It mostly damages the country itself. It means that the country can't be relied on for contracts for internet service. The internet becomes very important economically, and so on and so forth. So when a government shuts down the internet within a country or part of a country, it damages the country. It doesn't hurt anybody else. The rest of us all route around it. The internet goes on. So what I would say about government shutdowns, by the way, the Internet Society has a project where they're measuring the economic damage that internet shutdowns do. That's mostly what it does, is it hurts the country that does it. Okay. Now, how can people get involved in the IETF and in the development of specifications for the internet? I'd be happy to mentor people in that. Basically, what they need to do first is get on mailing lists, which is something that you can do from home, join conversations that are ongoing, contribute to them, and then maybe as a next step, file documents and allow their own ideas. And how does the internet affect me? How does this technology affect me? And get involved in that level of discussion, which I would strongly encourage Drew that's been involved in that. There are a number of people that are here in the room that have been involved in that. So, yeah, it's a conversation. Get involved in the conversation. Let me turn to you.
Yeah, hi, I'm Janice from India and I'm an IoT developer by profession. So I have a very specific question. So for instance, there's somebody like me who's a newbie and who is into development. My main time role is development, but I'm also interested in research. So there's IRTF, which is taking care of the research track. So can you throw some light on how somebody can get involved in most of the research areas which happen, and what is the difference between IRTF and IETF particularly?
So a researcher is fundamentally concerned about questions. An engineer is fundamentally concerned about answers. And so the IRTF is looking at what's next and what's coming down the way. If you want to look at IRTF involvement, I would suggest that you go to www.irtf.org. And you'll find there a list of, I want to say 19 or 20 research groups. Click on one that looks interesting, thing-to-thing networks or whatever. And you'll find information there that describes the group and tells you how to join it. And then you can be involved in their email discussion. You can submit papers. You can do things there. IETF, similarly, you would start at IETF.org. And go down into whatever working group. So
Another
I'm running out of time.
Hackathon is another one good place for developers to take part in IETF. Hackathon.
Yeah, hackathon. So what a hackathon is an environment in which we get a bunch of engineers in a room and looking at a problem and looking at some code to go do something about that problem. And what that does is it gives people a chance to have some familiarity with the code and perhaps meet some of the people that are involved. In conversations, one of the most important things in any conversation is knowing who you're talking to. And that gives people an opportunity to do that.
I am Arnab. I am working with TCS. The question that I have is that with the advent of say quantum computing, is the basic nature of internet going to change?
What do I think about quantum computing? Well, to begin with, there's an IRTF group on that. It's something that people have been playing with for years. They haven't quite figured out how to do. They haven't quite figured out how to use. But things are moving along. And so at some point, it's going to be an important part of computing. If there's a place that I would suggest that a PhD candidate go apply his or her skills, that might be a place.
Good morning, Anupam Agarwal from India, and I also work in TCS. China is working on IPv9. Is that a reality?
So when it comes to China, China has been, since the late 1990s, has been trying to figure out how to not have to have communications technologies designed in the West. They want one that is specifically Chinese. And so they've been working on things. So far, they haven't been successful. They have some very good engineers there. Please don't understand that as a statement that the engineers aren't good, or that the companies are incapable. The government has a few problems. I'm not going to get into the politics, but that has been going on. So,
Thank you.
Thank you.
Thank you so much, Fred. Let's give Fred a hand.
Fred will be back later to tell us about the principles surrounding the internet, and that's a very, very interesting conversation too.